Okay, I think it's time to start, right? Ina? Disappeared. Okay,
Let's
so
wait. Let's wait to enough. A minute. Let's give the chair introducing you the opportunity.
the chair has disappeared.
Yeah.
I'm here.
Okay, so
Yes.
so I will start.
No. I will introduce you.
You will
I can
introduce.
Ina,
Okay.
Ina is here.
Thank
Ina
you,
is
Eli.
Yeah, no. Everybody should be introduced. So I am very
But
happy
Ina is here. Ina is
to see
here.
you. You are here. Okay, go ahead.
Okay, so it's a pleasure to introduce next speaker. So the next speaker is Miriam Cohen from Ben Gurion, and she will speak about conjugacy classes and representations of Hopf algebras and the quantum doubles.
Thank you. First of all, shalom to all of you. It is a great honor for me to lecture in this meeting, recognizing my very dear friend, Amitai Regev. We have met many years ago when we were both PhD students at Tel Aviv University. None of us have really studied at Tel Aviv University. We belong to other universities, but we were office mates there. And one day, Amitai had this brilliant idea to introduce me to Yitz Hershstein, who was just joining the Weizmann Institute. He thought that he will stay in Israel for many years. Of course, he left some years later, but I was lucky enough to meet him, and it changed my career. I wish to thank you, Amitai, for having this brilliant idea and for your matchmaking and for being my friend for so many years. So I will start with my lecture, which is Conjugacy Classes and Representations of Hopf Algebras and their Quantum Doubles. It's joint work with Sarah Westreich, with whom I'm working for many, many years together. Semi-simple Hopf algebras over algebraically closed fields of characteristic zero have an elusive nature. On one hand, they resemble finite groups or groups algebras, and in many aspects, they do resemble, and as a result, many of the techniques in dealing with Hopf algebras try to use methods of group theory and their representation theory, sometimes with a great deal of success. On the other hand, many elementary facts about finite groups are either hard to translate or even false. You have to somehow get a feel for what would work and what would not. For example, finite groups, you would think that finite dimensional Hopf algebras are the analog of that, but that doesn't always work. A common key feature of groups and Hopf algebras is that the tensor product V tensor W of two H modules becomes an H module. H is the Hopf algebra. In a non-trivial way, by using the co-algebra structure of H. Hopf algebra, I will, in a moment, I will say what are the main features of it. And Hopf algebra has both a co-algebra structure and an algebra structure. And using the co-algebra structure, we can talk about the tensor product in a very natural way. This resembles is even stronger when H with an additional structural, not a constant, an R, which is an element of H tensor H, is quasi-triangular. In this case, V tensor W is really isomorphic to W tensor V as H module, vis-a-vis the R matrix, which belongs to H tensor H. This, in a certain sense, is the essence of being quasi-triangular. Throughout, as I said, H with the mu multiplication, delta co-multiplication, S called the antipode, and epsilon, the augmentation map, is semi-simple, hence finite dimensional Hopf algebra over an algebraically closed field of characteristics 0. And here is the multiplication. The important is that the delta, this is the notation which is used was used by Sweedler and made things quite easy to use. Otherwise, it would have been a big mess, because once you do delta again on the first one or delta on the second one, things start to go haywire. And this notation makes it much easier. The antipode, S, is an anti-automorphism of the Hopf algebra, and the augmentation map is a map from H to K. We know the augmentation map also for group algebras. The dual home HK is also a Hopf algebra, where the multiplication is the star of delta and the co-multiplication of the star of mu, etc. And again, when H is semi-simple, so is H star. The Drinfeld or quantum double of H, D of H, is the tensor product algebra, or D of H star cop, where the cop means that the delta, instead of doing delta H summation H1 tensor H2, delta cop of H is summation H2 tensor H1. In other words, you twist it. It has a Hopf algebra structure, and it is always quasi-triangular via the image of the identity under this isomorphism. When H is semi-simple, again, so is D of H. These are all results of Redford many years ago. We denote by P bow tie H an element of D of H, P in H star and H in H. When applied, the double construction. Pardon? Okay. Somebody is talking there. I will go back and forth between KG and H just to give you some kind of a motivation. When you apply the double construction to KG, the group algebra, G a finite group, G will always be a finite group. With PG, the G's projection is a basis of KG star, which is dual to the elements of G. We have PH bow tie G times PH prime bow tie G prime is this. So it is quite easy to multiply when you are in KG. It is much harder to multiply when you are in D of H, H and regular Hopf algebra. The module structure played a central role in this context. H is a left H star module via the hit action. This is really a left hit action, a right hit action. And this is how it is defined. P applied to A, P prime is A, P pre prime. And H is a left H module via the adjoint action. Here comes the word adjoint, which is similar to groups. And when you look at groups, delta of G in groups is G tensor G. So this, and S of G is G inverse. So when you take G, add A, you get G, A, G inverse, which is the regular adjoint action. But with Hopf algebras, it's not so easy. This is the adjoint action. The combination of these two actions make H into a DH module, and this is what we are going to use throughout. P bow tie H bold A, you apply H to A via the adjoint action, and then you right hit with S of P. If rho V is a representation of H, then its character, as we all know, is given by the trace of rho V of H, rho V of H. The product of two characters is given by the character of the tensor product, and the product is an integral sum of irreducible characters of H. As for groups, the character ring is a ring with involution chi v star is equal to just chi v star. We define the character algebra RH to be the subalgebra of H star generated by the characters of H. It turns out that R of H is the algebra of all co-commutative elements of H star, that is delta of X is delta cop of X. Delta cop, as I mentioned before, is you just switch between H1 tensor H2 to H2 tensor H1. The involution coincides with the antipode S. The set of irreducible characters form a basis for RH. When H is quasi-triangular, then RH is a commutative algebra. This is a result of Drinford. A theorem about 30 years ago by Katz and Zhu is that when H is semisimple, so is RH. So it becomes, in the presence of quasi-triangularity, R of H is something quite easy. It is a commutative semi-simple algebra. Now, throughout, we let V0 up to Vn minus 1 be a complete set of non-isomorphic irreducible H modules of dimension di, and E0 to En minus 1 and chi0 to chi n minus 1 be the associated central primitive idempotents and irreducible characters of H, respectively, with E0 is lambda. Lambda is the idempotent integral of H, and chi0 is epsilon, the same epsilon that we have mentioned before. And we have lambda, which is chi of H, the regular representation, chi with respect to the regular representation of H, to be summation di chi I. And it satisfies lambda of lambda. This is little lambda, and big lambda is equal to 1. When RH is commutative, it is also a basis of central primitive idempotence. And this is the case when we have mentioned before, the idempotents are denoted by Fi, I from 0 to n minus 1, where F0 is 1 over d lambda, d the dimension of H. And now comes the first definition after the long introduction. What is a conjugacy class? We have defined the conjugacy class, the ith conjugacy class, as Fi H star hitting the integral. Now, this looks very bizarre. We have shown that Ci is an irreducible D of H module via the action bold that I've mentioned before. And moreover, H is a direct sum of these conjugacy classes. And this is how it is a direct sum of irreducible DH modules. We generalize it also to class sum. Again, it's something taken from group theory. Ci is dFi applied to lambda, and eta I is Ci divided by the dimension of FIH star. Now I will show you what it means for groups. We take H to be Kg. It is a quasi-triangular Hopf algebra with R equals 1 tensor 1. Now the group algebra is in H star, and Kg star is a commutative ring. So it is commutative. And the projections PG that we have mentioned before are a basis for KG star. We have lambda, the integral that I've mentioned, is something that many of us know, a very typical element of a group algebra. It's the summation of all G, G, and G divided by the order of G. This makes lambda into the idempotent element. And PG prime applied to G is just the delta G, G prime, G. In other words, it's 0 when G is not equal to G prime and 1 when G is equal to G prime. And for sigma I in G, we have sigma I, which is usually denoted by the conjugacy class of sigma I, which is the set of all G, sigma I, G inverse. This is sigma I for groups. And Fi is something that not so many of us know, is just summation PG, where G is an element of the conjugacy class. And indeed, when you take the order of G, which is D, which I've mentioned before, summation PG, this is the Fi. And when you apply it to this, which is lambda, you get the sum of GG in Ci, which is Ci. And when you take this, you get, this is Ci, the conjugacy sum, and this is the conjugacy class. So once I've shown you what it means for groups, there is one more element which is important, which I'll mention. It's the normalized class sum, which is the class sum divided by the dimension of the conjugacy class. When HR is quasi-triangular, we have the following maps: FR, which is mentioned here, and FR tau. R is summation R1 tensor R2. R is the element which makes H a quasi-triangular Hopf algebra. These two maps are important. And then you have a Drinfeld map, which is a combination of these. And this is the Drinfeld map. And H is factorizable if the Drinfeld map is a monomorphism. This gives rise to a Hopf projection from the double of H to H, which is defined this way. And its dual is a Hopf injection from H star to DH star. And it is given this way. In particular, if Vi is an irreducible H module with associated character chi, then it is also an irreducible DH module because of this, with associated character phi star chi, which is an element of the character algebra of D of H. In order to distinguish throughout in what I will be talking about between H and D of H, elements of the D of H theory will usually appear with a hat. And so for D of H, the following sets have the same cardinality and the same set of indices. Chi I hat, which are the irreducible characters of D of H, etc. And eta I hat is FQ of hat, chi I hat divided by DI hat. This is something that was proved by us. So if we take the F of FT denote the set of primitive orthogonal idempotents of RH, since phi star is an algebra injection from RH to RDH, we have that phi star of FT, which we denote by phi hat of phi hat T, is an idempotent in RDH. And hence, for each primitive idempotent Fi hat, there exists a unique T, so the multiplication is that, and that means that Fi hat belongs to F hat, Ft hat. This defines an equivalence relations on Fi hat on all the primitive idempotents of the Hopf algebra of the group algebra of D of H by this relation. Fi hat is equivalent to Fj hat if the multiplication is Fi. In other words, Ft hat has Fi hat as one of its summons. You see, because Ft hat was a primitive idempotent when it was in R of H, but it is no longer a primitive idempotent when it is in D of H. We denote this equivalence class of indices by IT. All of the equivalents will be in an equivalence class IT. And we have the following lemma. If the eta j hat and eta t are the sets of normalized class sums in DH and H respectively, then phi, the map that I've mentioned between D of H and H, if it is equal to eta of t, then it means that J is then in the equivalence class IT. Important elements of IT are the chi hat, the characters, which we denote by JCT, the character of the irreducible DH module CT. Remember, I told you that the conjugacy classes are irreducible DH modules. And so this is how we denote them. And this is what they are. And motivated by that, there is a theorem, which is written here, that the conjugacy class, if we take its character in D of H, when you take phi FQ hat of this element, you get eta T. Hence, by the previous lemma, which was just here, once we have something equal to that, that means that J is equal to IT, is an element in the equivalence class. And that, by the previous lemma, JC upper T, J of the conjugacy class, is an element not of IT, but of IT star, where T star means that we are not looking at T, but at S of T. Another equivalence relation arises from Nichols-Richmond equivalence relation on characters. Now, the motivation of the Nichols-Richmond equivalence is that if we take Hopf subalgebras of KG star, they are in one-to-one correspondence with normal subgroups of G via the representations of their quotients. Explicitly, each Hopf subalgebra B of KG star is of the form KG of N G over N star for some normal subgroup G, and some normal subgroup N of G. And given a normal subgroup N of G, we have a natural equivalence relation on the irreducible characters of G, where each equivalence class consists of all irreducible characters with the same restriction to N, up to scalar multiplication. This equivalence relation is now expressed in the Nichols-Richmond definition. Let B be a Hopf subalgebra of H star, again, instead of being as a Hopf subalgebra of KG star. Define an equivalence relation on simple subcoalgebras of H star. Subcoalgebras which are simple, they don't contain any other subcoalgebra, as follows. Bj is equivalent to Bk if and only if Bj is contained in BBK. Denote the equivalence class of Bj in such a way, and so that the Nichols-Richmond equivalence yields a decomposition of H star. H star is the sum of B, Bt, where Bt is one of the representative of the equivalence class. And since each simple subcoalgebra Bj is generated as a coalgebra by the irreducible characters, chi j, we have an equivalence. Chi j is equivalent to chi k if and only the integral of the Hopf subalgebra B, lambda B, chi j divided by the dimension dj is the same as lambda B chi k divided by dk. So we have another equivalence class. And now what is interesting is the following. Back to dh, we set n hat dh co-phi. This is the definition of what is dh co-phi. It is really the analog of kernels when you go back to group theory. And we take B hat to be the Hopf subalgebra FQ hat inverse of N hat. Now FQ hat inverse exists because, as I said, DH was factorizable and FQ hat was a monomorphism. And when we take T to be another object, R tau inverse, HT is also quasi-triangular. And so we can define FT, phi-t, and FR the same way as FR phi before. And we have proved that B hat is actually equal to phi-t star of H star. And we show that JK is in the equivalence class IT, as I've mentioned before, with the FI and with the conjugacy classes, whenever chi j is equivalent to chi k hat. And we have said that each IT has a special element. It has a special element which is related to the teeth conjugacy class with the index JCT. And so the main theorem now is that if HR is a semi-simple quasi-triangle Hopf algebra and CT is a conjugacy class, and chi hat indexed by JCT is in the algebra of RDH, its corresponding irreducible character, and B hat be the simple subcoalgebra of DH star generated by chi hat JCT, then DH star is the sum of B phi-th star B hat JCT. Hence, each irreducible character of DH is a constituent of phi-t star chi hat JCT for some irreducible H character chi and some conjugacy class CT. Equivalently, each irreducible DH representation is a direct summand of VI tensor CT, where VI is an irreducible H representation and CT is some conjugacy classes. The special case of one-dimensional representations of H is of interest. And I don't think that I will have a lot of time to go into it, but one can deform an action by an eta which belongs to G of H star. G and eta, G of H star are the algebra homomorphisms of H star. And this is a new sort of a deformed action. If before H acted on M, now it is deformed by eta. And now we can take FR of eta inverse tensor eta. This will now belong to G of D of H star. This is the result of Redford. And hence, as a result, we have a deformed bold action on the conjugacy class, on NEC, and this is the way it is defined. Based on the above, we obtain a family of irreducible DH modules that are modifications of CS on one end and have the form VI tensor S, CS. Let eta be an element of GH star, then H lambda eta inverse. This is how eta inverse acts on lambda. CS is just the conjugacy class, which is deformed. In particular, the one-dimensional module K lambda tensor CS is just equivalent, just isomorphic to CS as a DH module. And I will just show you one example, the representations of DKS3. S3 is the group generated by 1, 2, and 1, 2, 3. And the conjugacy classes, as we all know, are these. And their centralizers are these. And the irreducible representations are given in this form. This is the sign operation that we all know. It gives the sign of the permutation. And these are the three representations of KS3, where this is E omega. And when we take the tensor product of a KS3, this is what we get. And I will just show you, I don't have the time to go over the details, but what is interesting is that these were all one-dimensional, and so you get CX tensor V1 to be CX, CX tensor VC2 is CX deformed by the sign, and here comes something new. This is our theorem. CX tensor V3, which was a two-dimensional module, becomes is no longer irreducible. It is a sum of two irreducible modules, and so on and so forth. This one is very interesting, and it is nothing that was mentioned before. So this is the example of our theorem. Thank you very much.
Thank you very much, Miriam. Let us thank the speaker. Any questions?
This identity, M4, a direct point with M5, direct sum, is it a part of an infinite family? Can you extend it?
No. This is what we have. I don't think that it is an infinite family. No.
It's very interesting. But do you think it can have analogs to other cases?
No. This is just the beginning of what we have been doing, and this is really the raw results that we have so far. And we do not have analogs. We are looking at some other groups, and we are trying to see what is happening in other groups with this sort of techniques.
Thank you. It's very interesting.
It was not trivial to prove it.
Yeah. Interesting.
So the parametrization is no more by partitions.
Pardon?
The parametrization of the reducible is no more by partitions.
I don't understand.
You started with S3.
I cannot hear it. I don't know. I don't understand what you're saying. The parameterization
is not by partitions.
It belongs to the partition. Yes, it has something to do with the partition. Yes, that is how all these things came up.
The split.
Sarah? It reminds me of blocks. It reminds me of breaking down to blocks in the modular theory. Some of the things you did. Maybe Sarah should speak to me about it, and I'll tell you what I'm trying.
This is a good idea. We may be looking at it. But as I say, we are looking at groups, and this would be a good idea, but our aim is really to do it for general Hopf algebras. But this is reminiscent of blocks, yes.
More questions?
Have you You know, Tzvi Arad, plus its memory, was working on table algebras, and which generalized the properties of character tables.
Yes. Yes.
Have you looked at any connection with those?
No, we have not looked at connections. We may be looking because we were looking for connections between table algebras and Hopf algebras some time ago. And we had some ideas about them. So we may be looking at that. That's a good idea.
Thank you. It's very, very interesting. Thank you.
Thank you.
More questions? So if not, let us thank Miriam again.
Thank you.